All right. Well, I think in the interest of everybody's time, we'll probably try to get this thing rolling. So thanks everybody who showed up. Again, Insight, we try to put on one of these about at least around once a month, talking about usually different applications and different products. And so we want to kind of focus this one on diluent and condi production, and then a bit about crude blending as well. And so like I usually tell people as I'm going through these, if you have any questions, feel free to turn on your mic, interrupt me, feel free to put them in the chat and I'll try to look for them, or Jaden will look for them. But yeah, any questions along the way, happy to try to address them. So again, we're going to talk about natural gas condensate, or condi. Diluent, as a lot of people talk about it because we use it for diluting bitumen a lot, and then a bit about the idea of crude oil blending. So I'm going to start this off as I usually do with a little bit of a summary of who Insight Analytical is, talk briefly about gas processing and what goes on, especially near the front side of the plant, near the inlet side of the plant. And then we'll talk a little bit about C5 plus, or condensates, required specifications in the pipeline, because it's really the fact that there's pipeline specifications that allows us to, or gives us some leeway to try to do optimization. And so we'll talk about how those pipeline specifications affect how much money you can make if you're running a gas plant, and how you can try to get to that point where you've optimized the facility to maximize revenues given the amount of the fluids that are coming in. And to do that, we're going to talk a little bit about how we would go about, or what we need to think about when we're trying to optimize our condensate stabilization side. And because, like we said, this condensate is often used as diluents, we also want to bring that into this idea of how do we apply this, the same technologies we're going to talk about, to crude oil blending. And the technology we're going to focus on is this near infrared analyzer from JP3. I've done a lot of webinars about the JP3 analyzer, so we're not going to talk about it that much in terms of how it works. Certainly, if you have any questions, or if you'd like to get more information about that particular analyzer, we have some YouTubes up, or videos up on YouTube, or send us a link and be happy to send you technical papers, all that sort of stuff. All right, so Insight Analytical. Insight Analytical is a Calgary-based systems integrator and distributor. So we purchase and resell analytical products, but integrate them into solutions and packages. We operate out of about a 20,000 square foot facility in the northeast of Calgary. We've got really good access in the facility, so we can bring full analyzer buildings in and out easily. We're for all Canadians here, I assume most of you guys are Canadians. We have certain pressure equipment requirements called CRN numbers. And so we're an AB83 compliant fabricator. We can build systems that have full CRNs, design products that have full CRNs. I got a great team that works for me. Lots of people I've been working with for a lot of years in different companies. So I've kind of brought some of the people that I know I can work well with, and I know are good at their job. So we have really good documentation, drafting capabilities. We design everything in SolidWorks first, so we can give you a 3D model of this is what we're going to build. Journeyman electrician, I should say journeyman electrical and instrumentation. So E&I guys, and we do full factory acceptance tests here in Calgary. We're equipped to run gases, run calibration fluids, etc. Don't know why that circle's not going away on my screen, at least. Not going away on yours, probably either. We have full systems integration capabilities. We will design anything from a small custom sample system to full process analyzer integration. If it's got a PLC in it, like this one in the background over here does, we'll develop all that PLC code, do full testing for that as well. everything up to doing full analyzer buildings. I always like to show this picture because it's a building that's got a JP3 analyzer in it, one of our automated grab sampling systems, composite samplers, solvent flush tank. So there's a bunch of our gear in there. And it's just a nice package we'll put together. We consider ourselves going to specialize on the analyzer sample system side of things. I've taught sample system courses for a decade or so, and we still do them. But we also try to view ourselves as a full service provider. So we will work with you on an analyzer project right from the front end engineering design to help you pick which analyzer to use, through detail engineering, through fabrication of the system, all the way up to field commissioning. And of course, service is a big part of it. We run service out of Calgary, out of Edmonton, out of Grand Prairie. We really try to stick to our knitting. We do analyzer projects, analyzer or analytical sampling projects, and that's it. So if it's not about analytical, we aren't your guys. All right, we're gonna talk a little bit about a gas plant. Real simplified overview of what happens when we're talking about natural gas production. So we can start out with this idea that there's some wells out there, perhaps a bunch of wells, perhaps wells from different producers, and there'll be some sort of gathering system that brings all the fluid that's coming from those wells. Again, if we're talking about natural gas production, these are probably referred to as gas wells, but really the fluid that's coming in isn't a gas. It's often three-phase, almost four-phase. Sand, if you like, sand, dirt, clay, water, some liquid hydrocarbons, and then some gas-phase hydrocarbons. So the first thing that usually happens is there might be an inlet slug catcher or something like that, but we come into what's usually referred to as an inlet separator. And there's a bunch of different designs. I happen to just show one here that kind of fit with the way I wanted to do this drawing. The inlet separator's job is to start separating phases. So we get water coming down at the bottom because it's the heaviest. We get gas going off the top. And I wrote two other stuff because it goes to other parts of the gas plant. It'll go to things like dehydration, sulfur removal, NGL recovery, compression. And the phase we want to talk about today is this one that's coming out the middle. And that's my hydrocarbons, my liquid hydrocarbons. And so in that phase, there'll be a bunch of the heavier stuff that's more oily, but there'll still be some of the lighter hydrocarbons. It's going to be determined by the vapor liquid equilibrium. The pressure that's in that inlet separator and the temperature is going to determine what's boiled off to the gas phase there and what's coming out as liquid hydrocarbons. We usually try to run it so it has a fair bit of light hydrocarbons still in it. So the next operating vessel after that is usually a thing that we refer to as a condensate stabilizer. If you're producing light crude oil, like in the US, you'll see the same sort of device and often be referred to as a heater treater. But it's to say they're doing the same kind of things. It's going to take this liquid stuff that came in, it's going to heat it up. And when it does that, it's going to boil some of the light ends, the things like the propane and the butane, C3s and C4s, and lighter hydrocarbons than that, the H2S, any natural gas that's still in there, the ethanes. Those should all go off on that green side, green being gas. And that'll go up into the rest of our gas plant. The liquid that's coming out of the bottom here is often referred to as stabilized condensate. And it's a pretty high value product. My pen stopped right there. There we go. Going slow. Condensate trades for about the price of a crude oil, it's like WTI crude. So it's a high value product that's made at the plant. That may go to tankage, excuse me. That may go to tankage, and then we're going to ship it out somehow. Truck it out, rail it out, or send it out to pipeline. But somehow we got to know what it's worth. How much are we sending out? So I added in over here that we're going to have a flow transmitter of some kind. So we know the volume of condensate that we're producing. And usually, especially if it's going up, there'll often be a custody transfer skid, a metering skid, and they'll measure the flow there, and they'll also take a sample there. Most often, if it's going to a pipeline, this is going to be a composite sample. So a composite sample is a sample that is built up as an average over a period of time, typically a month. Put a little star beside there because that sample is the star witness. There's specifications related to this pipeline. Pen's working fine. There's specifications related to that pipeline. And depending on how we meet those specifications or how close we come to those specifications is going to determine what the value of that condensate is. So that sample is sent to the lab, say once a month, and they get an analysis of that sample, and the operator of the pipeline or the transportation system will look at the results from the analysis of that sample and determine what's really the value of that product. You know, there's a base price. We see it every day. The price of oil is this. Not oil is worth the same. Condensates and oils are quite different. And so in the terms of their compositions, and certainly in terms of some contaminants. And so things like the density of the condensate, how much sulfur is in it, and how much butanes are in it, are going to determine really what the value of that condensate is. So, and the pipeline guy has specifications, and one of them is you can't put too much butane in. The specification can't have more than 5% C4s in there, C4 minus, C4s and under. And so you would think, well, one of the ways then to make sure I'm never off spec is to just make sure I boil all those out. But if I do that, it would mean that I push all of the C4s over to the gas side. And if I do that, I produce less liquids. Those liquids are worth a lot of money. So I want to find that optimum place. I'm stuck in this balancing act where I would like to have as much butane in there because that increases my volumes. But if I have too much butane in there, I'm going to pay a penalty. So whenever we have that competing kind of trend between two things, more butane is good, it gives me more volume, but too much and I pay penalties, it means I'm in a position where I can do optimization. I can try to find the sweet spot where I can make the most money. So we have a whole infrastructure that's built around this idea of condensate equalization. We call it equalization because we kind of want to balance out that not everybody's condi is the same and pay people who give us really good condi more money than people who give us condi that, say, has poorer specifications. The main specifications we look at for condensate are its density, and the spec is 750 kilograms per meter cubed. If your condensate is more dense than that, you'll pay a penalty or they'll reduce the value that they pay for the condensate. But if you're less dense than that, you'll actually get a credit. So there's no benefit to you to necessarily try to make your condensate more dense, because you actually get a credit if your condi is light. Similarly with sulfur, you're going to start paying a penalty if you're over 0.2 weight percent, but if you're under 0.2 weight percent, you're going to get a credit. So both of those, there's no real value to or not often as much value as trying to purposely adjust those parameters. You'll get credit if you're under the specification and only pay penalties if you're over. But for this thing that they call deemed C4 minus, and I can explain exactly how you calculate deemed C4 minus on the next slide. Essentially, it's how much butane. The spec is that we have to be under 5 liquid volume percent. The penalty, if you're over 5%, is large. Basically, they say, anything that's over 5%, we're not paying you a penny for that. So if you're 6% butane and the spec is 5, so you're 1% over, they say, I'm only going to pay you for 99 cents on, or 99 barrels of every 100 barrels of condensate that you give me. Because 1 barrel was too much butane, and I'm not giving you anything for that. But there's no credit if you're under. So, because you might say, well, I don't ever want to pay penalties, so I'll run my condensate stabilizer, so I'm always under the specification. I don't get any credit for doing that. But if I do that, by being under on the amount of butane that I'm allowed, I end up producing less volume of condensate. So if my specification was 5% and I run my plant at only 4%, I've basically said, I'm only going to produce 99 barrels when I could have produced 100. If I produce less volume, I get paid by the barrel. So if I produce, or by the meter cubed, if I produce less volume, I make less money. So basically it means the penalty for being under is as large as the penalty for being over. If I'm at 6%, I don't make 1% of the money I could have made. And if I'm at 4%, I don't make 1% of the money I could have made. 1% may not sound like a lot, but we're going to go through an example for a fairly large gas plant, but not atypical, and see that 1 or 2% can be $300,000, $600,000 a month. So when we talk about deemed C4 minus, the way the specification has been written is we take the 2 isomers of butane, so IC4 and NC4 are the butane. We take how much butane is in the condensate and add 3 times the sum of the methane, ethane, and propane. So to know what the DMC4 is, we have to know those 5 specific, the concentration of those 5 specific hydrocarbons. We have to know how much methane is there, how much ethane, how much propane, and how much of the 2 different types of butanes, and then apply that formula and calculate the DMC4. If it's greater than 5%, anything greater than 5%, you get 0 value for. So if you're at 6%, they would say, hey, you ship me 100 barrels, I'm going to pay you for 99 of them. But that 100th barrel, that one at the end, I'm not going to pay you anything for that. So similarly, if you're under 5%, you've produced less volume from the stabilizer. You don't get paid anything for volume you don't produce. So again, the penalty is 100%. So what you need to do is you have to try to run that stabilizer to stay as close to 5% as possible. And people will tell you they're going to do this by saying, well, we know if we run the stabilizer at 60 degrees and 200 pounds, our condi is on spec. It is for the one time that you did the test for the stuff that was coming in the plant that day. But as we, especially now with the way we bring wells on and shut wells in and bring in different producers, the stuff coming into the plant is changing all the time. So the optimum operating conditions for that condensate stabilizer change daily, change hourly. So here's a sample of how that equalization calculation for the DMC4 works. And this is from an actual plant. It's from a client we're talking to about trying to optimize their stabilizers. They ran a sample, or their composite sampler that is controlled by the pipeline, took their monthly sample, sent it into the lab, and it turned out their DMC4 was 6.95%. The price of condensate in that month was $689 Canadian per cubic meter. So we can then calculate how much their penalty is. They were 6.95%. We subtract the 5% they're allowed off. They're 1.95% over. Multiply that by the $689 per meter cubed. Comes out to almost $13.50 a cubic meter. So for every cubic meter of condensate that they put out in that month, they paid a penalty of $13.50. This plant's producing around 1,250 cubic meters a day. If you multiply that through 30 days, 1,250 cubic meters a day, almost 1,350 a cubic meter, that month, the penalty they paid for being over on their condensate was $500,000. So you got to think there's some value certainly in trying to not run over. And how do you know you're not running over the value if you're not doing the measurement? So there's value in measuring the DMC4. Let's look at it from the other side as well. So I've gone through a calculation again for running under. And I also, so you'll get a copy of all these slides, and these will be active hyperlinks in the slides, the things in blue. So there's a website that is run for Alberta for the crude and condensate calculations for how you calculate what your penalties or credits should be. So there's a link to that spreadsheet, and every month they update what the value of condensate is and some of the other parameters. So this link gets you the most recent month values. You have to change some numbers in the spreadsheet. So you'll also get an email after this with a copy of that spreadsheet, the one direct from the website, and also a copy of that spreadsheet where I did the calculations you saw on the previous slide. Excuse me. So let's take a look at what that equalization would look like if you ran under. Suppose I said, I don't want to pay penalties. So I'm going to make sure I run my condensate stabilizer a little bit hot and I boil stuff out really well. So my DMC4, instead of being 7%, I've brought it down to 4%. Well, 4% is less than 5%. I don't get any credit for being under, but I don't pay any penalties either. So there's zero price differential. I get $689 now for my cubic meters. My plant's capable of producing 1,250 cubic meters a day if I'm at 5%. But if I ran 1% lower butane, I had 1% less production. So that would mean my production in that month would have averaged around 1,237.5 cubic meters a day. Sorry, I don't math, but you kind of have to go through this calculation to see where the value comes in. By having 1% less production, my plant made about $25 million worth of condensate, 25.5, but it should have made 25.8. If I'd run at 1250 instead of 1237.5, I would have made 25.8. My lost production was $250,000. So you might, when I've had people say to this to me, well, when we look back at our composite sampler results from the previous year, it averaged out close to 5%. That's not necessarily good. If you were 6% one month, you paid a whole bunch of penalties. And if you were 4% the next month, you had a whole bunch of lost production. It doesn't average out in the dollar values. So what you really want to try to do is not have months where you're over by too much and not have months where you're under by too much. The only way to practically do that is by continuously measuring what the DMC4 is at the out of that condensate stabilizer and optimizing your temperatures and pressures based on composition. You can't do that by sending samples to the lab. The lab's going to take a week to get you some numbers. Oh, a week ago I was running too high. You're going to have to put an online analyzer. So optimizing stabilizers is going to require that we measure the composition. And people will say, oh, great, I'll put a gas chromatograph in. Gas chromatographs are wonderful devices. Accurate, precise, repeatable, but they're gas chromatographs. This is a liquid sample. And we can try to vaporize it. And on some condensates, that will work. The problem is people hear the word condensate and they look at the chemical compositions of samples and they go, oh, I think I can get a GC to work on that. This is a natural gas condensate from a debutanizer. Crystal clear. It's got no dirt in it. I could just about run my lawnmower on this. This is natural gas condensate. This is the stuff that comes back from the US after they've stripped the condensate out of the bitumen we sent in there. You can see it's kind of yellow and dirty, but still pretty, pretty nice looking. Looks like it might not be that hard to get it to run through a system and not plug things off. This is a natural gas condensate out of a condensate stabilizer at a gas plant. And now it's starting to look a bit more viscous, dark, dirty, ugly. This is the sort of thing that plugs analyzer sample systems. And when it gets into GC inject valves, it plugs GC inject valves. This is natural gas condensate. It's from the Enbridge main line, what's called CRW. This is a sort of quantity that can be very difficult to work with in an analyzer because, again, it'll plug off the sample system. You're changing filters every day. You get one slug of waxer come through and your injection valves and your GCs are dead. So the problem is when we get to gas plants and we're at the bottom of that condensate stabilizer, if you think about back to that slide I had, let's go back and look at that for a second. The stuff that comes into the condensate stabilizer comes off from near the bottom of that inlet separator. So all of the sand, all of the clay, all of the heavy, dirty stuff that's coming in from our wells is in those liquid phases. We push it over to the condensate stabilizer and we come off the bottom of the stabilizer. That's where all the heavy, dirty, nasty stuff settles to. And so now if we try to say, oh, well, I'm going to go and put an analyzer in right here. That analyzer is seeing all that dirty, nasty stuff. And so what we find a lot of times is that people who've tried to implement analyzers in these applications, they understand why they want one there. They can see the value of it, but the experience has been, we tried it and it didn't work. And so we've dealt with a lot of clients who've been in that sort of position of, you know, we try to put an analyzer, it doesn't work. When we used things like traditional vapor pressure analyzers or traditional chromatographs, the fact that they have almost always, they are lab instruments that have been converted for field use. They have tiny tubing, little tiny injection valves, lots of filtration and components in the sample system. And all of those things lead to very high maintenance and operating costs, if they work at all. We've worked with people who worked for 2 years to try to get a GC working on a stabilizer bottoms and finally just said, done. Can't put any more time into it. So I'm going to give you a teaser. I'm not going to talk quite about the analyzer yet, but I'm going to talk more about what we're able to measure with it. Insight Analytical started in 2016 to bring JP3, a company out of Austin, Texas. I was working with them as a consultant. I started Insight Analytical to bring JP3 up to Canada. It's an inline near infrared spectrometer. So I'm going to talk about this a little bit later. It does the measurement of liquids or gases with no moving parts. You don't have to filter the stream. You can run multi-streams on one analyzer. It's near real time, has virtually no maintenance. You know, once I get to here, I just did a presentation for some people yesterday. I used the slide to kind of joke about the old vaudeville and snake oil salesman. And when you're an analyzer guy who says, my analyzer has no maintenance and it's real-time measurement, people start to go, the guy's got to be lying to me. It sounds too good to be true. We've really got, you know, again, we've talked to us, we've got lots of customers we can say, look, talk to these guys. They've done exactly what we're doing. Cool things about this analyzer as well, which unfortunately it's not shown in this picture. There's a satellite, there's an antenna sitting over here. We have a cell modem connection. All the data that's going to it from it is in the cloud. We can log into any analyzer while it's out there and look at how it's running. We've literally called clients and said, you got water in the bottom of your condensate stabilizer right now because we can see a water peak in your infrared spectrum. And we run support for it out of Grand Prairie, Edmonton, Calgary. So how does it do when we try to measure something like Condi? So here's some data from a condensate stabilizer. These are lab values along the x-axis, and there's two different x-axes. This one is for the butane, this is the propane, and the isobutane. Top one is normal butane. So all the propane values are in blue. There's a cluster of propane values. Again, X was the lab. This y-axis is the online analyzer. So you see they have good agreement, linearly correlated. When the propane goes up on the infrared analyzer, the lab propane results went up. The green is on this axis as well, and this is the isobutane. Similarly, again, almost a one-to-one correlation between what goes on in the lab. And yes, there's some scatter around there. We have to remember there's scatter in the lab results as well. But we're measuring the propane, the isobutane, and then the red ones are the N-butane. And and we're measuring those against this axis. So we've got the same lab results that the pipeline company or who's ever deciding your penalty is being used on one set of axes and the analyzer result on another. And what we see is that we essentially have a 1-to-1 correlation between them. Yes, some noise, typically better than about 0.2 liquid volume percent. So now, these are the individual components. The thing that we get penalized on is DMC4. So here's a typical set of DMC4 results. The plant wants to run right around here, 5%. And so usually when we're setting the analyzer up, we purposely have them run off spec somewhat. So in this case, we had them run as low as 2, as high as about 6.5, because we got to make sure the analyzer is working well across that linear range so that we know if I get a reading up here, I have to change something in my stabilizer to bring it back around this point. Basically, on this set of data, the near infrared analyzer matched with the lab to within plus or minus about 0.14 liquid volume percent. So that would mean if I kept it running at 5 all the time, I'm somewhere between 4.85 and 5.15. Remember, this is fast real-time updates. The person that the product is going to is getting a monthly average. So some of the advantages the analyzer provides you is, suppose it had a problem at the plant and one of your reheaters for the condensate stabilizer was down, or you had some issues with getting the condensate stabilizer hot enough. So you ran down here for a few days. Well, if you know from the analyzer, I ran around 3.5 for a few days, that pipeline guy is going to get a monthly average. I'm purposely going to run up here for a little while and balance that out again. So I know that I produced 3,000 cubic meters that only had 3.5% butane in it. I'll make sure that I run high on butane for a little while and let that average out at the end. Then I can produce a bit more volume. The analyzer lets you deal with other plant upsets as well, because they may affect how the condensate stabilizer is running. So you gotta think, well, and so some people have argued with me, well, the money can't just go away. I didn't just lose the money. The money had to go someplace. And it did. The question is who's getting the money? There's an opportunity here to blend, say, a high butane condensate into a low butane condensate and bring that volume back up again. So, for example, if I'm a midstreamer and I know that I've got a whole batch of condi that somebody paid a penalty on, they were at 6%. Well, I just look for another batch of condi that's only 4%, and I put the two together, and now it's on spec. 4% from this guy, 6% from this guy, it averages out to 5. So I make the analogy sometimes, this whole blending thing is kind of like watering down the whiskey. You can take a low value product or lower value product, mix it in with your high value product and sell your low value product as if it was a high value product. And that's where a lot of the money is made. There's money to be made if you as a plant operator can optimize your stabilizer, or if you have multiple stabilizers with an online analyzer. There's also money to be made if you as an operator, and we have a client who does this, they truck in condensate from some other facilities, and when it comes in, they measure it, and they go, oh, this stuff's off spec. We're going to store it in this tank. And then they produce some of their own, and they just go and they put it in tankage, And then what they do is they go, I got a tank over there that's got too high a butane. I got a tank over here that's kind of low butane. Let's blend those two together and sell it all as on-spec product. And so to do that though, you have to be doing the analysis. If you're not doing it at your plant, someplace further down the food chain, there's somebody else who's bringing in product and saying, hey, these guys left me an opportunity to blend. These guys are low on butane or really low on sulfur, so I can blend some of my high off-spec stuff into their low stuff and produce a whole bunch of stuff that's right on spec. So there's a couple of places where money gets made here. And so now we're speaking about blending. We're talking a little bit about crude oil blending as well. So in blending, what we want to do is take a less expensive product and be able to sell our less expensive product as if it was a more valuable product by blending it into another one. So I kind of draw the little Goldilocks analogy at the bottom here. If I'm talking about vapor pressure and crude, Goldilocks comes along and says, this one's too hot. Oh, this one is too cold. Mix them both together. They're just right. So I can do things like take a very live, high vapor pressure crude and blend it into a dead or low vapor pressure crude and just try to meet my vapor pressure specification. Or I can take my off-spec high vapor or high butane condensate, put it into my on-spec low vapor pressure or butane condensate and make more volume of on-spec product. I can even take my condensate, if I know that it's very low, if I know that naturally my condensate stabilizer doesn't produce condi with high levels of butane in it, well, I can buy butane from somebody else and blend it right into my condensate. And do the same thing. I can blend butane into my crude oil. There's a specification on crude oil as to what vapor pressure it's allowed to have. If my vapor pressure specification is 90 kPa and the crude I have is only 70 kPa, well, I can add some butane in there and bring that vapor pressure up. The advantage being that butane might cost me 30 cents on the dollar for what a barrel of crude is. So I take this inexpensive butane, put it into my much more valuable crude, and I sell the inexpensive butane as if it was more valuable crude oil. And the same thing when we're looking at things like diluted bitumens. In Canada here, we produce a lot of bitumens from the oil sands. That bitumen, to be able to be transported down the pipeline, has to have a diluent added to it, has to make something added to it so it's not so viscous. Undiluted bitumen can have the consistency of like peanut butter. It doesn't flow down pipelines. So what we do is we add a whole bunch of condensate into it to dilute it, to make it so it can flow. But if it's still below the vapor pressure specification, we can go, well, instead of put a condensate in, now I'm going to add a bit of butane in and try to put cheaper product in and still make my stuff flow as well and meet all my specifications. Every one of these blending operations has one thing in common. More money, more money, more money. It's all about how can I increase the value of the product. So when we look at doing this in conventional oil, again, to try to give you an idea of how this runs, X-axis, conventional vapor pressure analyzer, Y-axis, near infrared. Oh, sorry, X-axis is lab. Y-axis is near infrared and also an online vapor pressure analyzer. So sorry, the blue dots, this is an online conventional RVP. Orange is the infrared. X-axis is the lab. So again, what we see here is that when we use this infrared technology, we can get results that correlate well with the approved lab methods, ASTM D6377 in this case, correlate well with a conventional online analyzer. The difference is it required almost no maintenance or calibration during the entire run. The infrared required no maintenance or calibration. So we can get better reliability. We also get 10 times, 20 times faster data. Updates every 15 seconds instead of every 5 or 10 minutes. It allows us to do better process control. So this is again, a vapor pressure in crude oil type example. It's the same thing, a vapor pressure in diluted bitumen. So lab at the bottom. Infrared on this side. Again, we see we get this nice one-to-one correlation. The blue dots, I made them kind of big and fuzzy like that to kind of show what the error of plus or minus 1 kPa would look like. Because there's error in the lab method. The lab method really says it's only good to 2.3 kPa repeatability. So when you see that they don't match people go, it doesn't match exactly with the lab. You don't know, well, is that because the lab was out by a little bit or the IR was out by a little bit? What was the real value? The blue dots are ones that we use to build the model. The red X's are examples that we're taking after to show how well the model continues to predict. So once we have these things calibrated and dialed in, the model continues to predict. Again, to within this case, we ran probably within 1.5 kPa or so. Okay, so we talked a bit about gas plants, about condi productions, about measuring DMC4 and vapor pressure, and briefly talk about the analyzer as well. So first of all, why do we use the near infrared? Well, by near infrared, we mean wavelengths of light that are beyond the red. So the visible spectrum's there. We're saying if we go more red than red and start looking at what happens as we move out there, what these lines are showing is how much of the light gets attenuated as it flows through a sample. So when I first started trying to pitch this to people, and I would say, I'm going to measure the properties of your condensate by shooting a beam of light through it. They know, have you seen my condensate? You're not going to shoot a beam of light through this. It's black. It's black because it absorbs all the light that hits it. It absorbs all the light in the visible part of the spectrum. As we get beyond there, it starts to transmit light. And then right around here, which is about a wavelength about 1600 nanometers, all the hydrocarbons start to absorb light. The hydrocarbons start to absorb light, and each one of the hydrocarbons absorbs light differently. So by the shape of the spectrum, we can figure out what hydrocarbons are there, and by how strong the spectrum is, we can figure out how much. So we sort of show it on here. The slide's animated. It's going to change on its own. Maybe a bit slower than I should have set up for, but so the top is what a natural gas liquids at a gas plant would look like, an ethane propane stream. The bottom is pure propane. So just looking at it, you can clearly see the difference. The top just changed to N-butane. You can clearly see how it's different than propane. The isobutane is clearly different from N-butane. Each one of them has a unique spectrum. And when we put it all together and make something like condensate, all those things overlap. But computers and pattern recognition software are really good at deconvoluting that kind of data. So then we take what we refer to as a flow cell. here. We allow hydrocarbon fluid to flow through it. Nice big port. I can stuff my pen through it. So we allow hydrocarbons to flow up through this thing. Inside it are two synthetic sapphire rods. They're crystal clear. The advantage of sapphire is it transfers infrared light really well, and it's the second hardest thing next to diamond. So it doesn't get scratched by sand. Then we connect fiber optics up to either end on these lenses. We shoot a beam of light through it. So my fluid is flowing between those two sapphire rods, kind of like the way it shows there. My fluid's flowing up. I shoot my beam of light through. The light interrogates the fluid. My software then says, how much of the light got attenuated at what wavelength? Let's figure out what's there. The advantage here is, again, when I go to a conventional analyzer, I'll often have things like 1/8-inch tubing, little tiny micro injection valves. It's not a problem with the analyzer usually. It's a problem with all of the things that have to let flow get in and out of the analyzer. Doesn't deal with dirt very well. These sapphire windows, dirt doesn't stick to them that easily. You can just wash it off by running toluene through the cell or diesel or something like that. So it's really easy to clean the system. Nice big ports that don't plug. With a conventional analyzer, I usually bring a sample out of the process and bring it all the way over to an analyzer building. It can change phase along the way. What we do with this is we mount that flow cell. That's the same cell I just showed you. We mount that out as close to the process that we want to measure as we can. We find some source of process differential pressure, maybe an orifice plate, process filter, a pump. Sample from the process returned to the condensate tank. And that drives flow up through the flow cell and right back down to the process. Very short line runs, so we get the fluid over there very fast, can measure quickly. That's put out near the process. Someplace else, we mount the box that has the spectrometer in it. Refer to this as being the brains, the whole thing. We don't put a dedicated analyzer building in. It doesn't have any process fluid to it. Process fluid staying out there by the process at the flow cell. We mount the analyzer in some place like an MCC building. Take fiber optics, shoot a beam out, bring a beam back. So these lenses that are on the side of the flow cell have a connection on them for it to make a fiber optic connection. We're not sending data over that fiber. We're actually sending the infrared light that we're using to measure the fluid and then bringing it back on another fiber. It gets back into the spectrometer. It measures that spectrum, how much light got taken away at different wavelengths, runs it through its software and says, oh, well, now I'm going to tell you what you want to know. We have to train it to tell you things, but we can tell you things like the viscosity, the vapor pressure, what's the C1 through C6 hydrocarbons in there. We can do this for gases or liquids with exactly the same system. The vapor pressure analyzer has exactly the same components as the DMC4 analyzer. Same flow cell, same spectrometer. Same flow cell, just slightly different length to measure a gas and a liquid. Same spectrometer. So the other cool piece of this is we can have this one, let's say, measuring condensate. And then we can attach another set of fibers and bring it to this one over here. Different color, maybe. Another set of fibers, bring it over to this cell over here. And this might be inlet gas to the plant. Weird, my pen doesn't keep up for some reason. Come on, key. So we can actually have, there's a version of this in the US that does up to 8 different measurement points. We've only used the version that does up to 4 here. So there's 3 versions of it. It's either 1, 4, or 8 measurement points. And so in Canada, we've only installed the single stream and the 4-stream one so far. Installations are really simple. This is a crude oil blending skid. So inside the building is the analyzer, the brains part. And crude is flowing out, flowing through the cell and returning back into the building. We have, this is where the infrared cell is. These little black pieces over there, those are the fiber optics. So that's the entire system for doing a crude oil blending skid. That white box that we saw on the previous page connected to this flow cell. So when we look at that condensate application in gas plants, we did a pretty simple thing. We went through and said, okay, let's go and check out AER data and find out how much condi all these plants produce. And what if we could increase their production by 1%? So we identified over 100 plants in Alberta that can make over $250,000 a year by putting one of these analyzers in. Some of these guys can make $500,000 a month. We're trying to reach out and contact them. If you're running a gas plant and you make over 100 cubic meters a day of condi, you should probably try to get a hold of us, because we can probably get an analyzer and they'll pay itself off in months. Identified about another 40 plants in BC as well. So there's a lot of these guys out there. From an installation perspective, we've got about 250 installs in North America. 40 plus of those are in Canada. A good mix of doing refined products, natural gas liquids, condensate, crude oil blending. So you can kind of see the big heat maps for it around every major oil field. You know, we've got Montney up here. We've got Marcellus down here. We've got the Permian over here. And so we've got a large, wide installed base right now. See, I'm hitting 1 o'clock, so I'm trying to go through this last little piece quick. Again, you're going to get a copy of all these slides. We talked a lot about this guy. Check out our website. Got a pretty wide range of products, everything from mass spectrometers to hydrocarbon, water and hydrocarbon dew point analyzers. And so there's a number of different products there. We can usually help you with an analytical tool for a large number of applications. And if we can do it, we're happy to recommend who we think can. So in summary, if you're looking at measuring hydrocarbons, contact us. We've got a lot of applications that have been developed right across the hydrocarbon processing industry, from gas phase applications to NGLs, crudes and refined fuels. Easiest ways to get a hold of us: visit our website, insightanalytical.com. Contact Lisa or myself if you're looking for more information, and we'd be happy to get it to you. That gets me to 1:03, so almost a 1 hour exactly, given we started 12:05. So if there's any questions, I'm happy to take them. Sounds like we're all good, or no one's left awake. Oh, there's a couple coming up in the chat. Oh, thanks, guys. All right, I guess if there's no questions, we will wrap this up. Like I say, you're going to probably get a follow-up aftercare email within the next day or so. And in that will be a copy of this presentation, the crude equalization information, and I think that's most of what's in there. Have a great day, everyone.